That's like smart. We're not prepared for this. We want to make some like, but it's gonna. We got the snow. Because we should check whether it apparently that wasn't it's like shorts and stuff. And we had to spend there like 2 days. Bro, I didn't. I didn't breathe. Any condition. Bro, that's what you do, bro.
All right, y'all.
That's crazy.
Was your breaks good?
I had problems.
I have I think second period, this doesn't apply to you, but sixth period, I have all your stuff graded and I've been graded, but I graded it over the break. And I was like, nice, okay, I'm done. And then I forgot to put it like in the grade book.
Oh.
But it's all graded and I'll put it in the grade book later today. So if you took a retake or something like that, it's done. I just forgot to put it in the computer, but I'll do it later today. And then I was gonna say some more stuff. But I don't remember what. But here, I'll just give you a little preview of what's coming up. Today and tomorrow, we'll probably finish the content of everything. We have 3 weeks until the test, by the way, like this week and 2 more. So we're in good shape. We're gonna finish content here, and then 2 more weeks of review, and then we're done. So the plan was originally to get through 10.8 and then be done with morning classes, which we can still do that if you want. That would be easier for me as well. But I think it might be good to have like some structured time to do review and stuff like that. So I'm gonna keep showing up, and if you guys want to come and do a review on just PC stuff, then we can do that. So plan is finish 10.8 and then keep coming in and doing a review, and I'll even keep recording it and you guys watch it at home even. And I think that's all I got to say for now. If I remember more announcements, I'll let you. But here is the last thing I taught you, which was 10.7. It was find the radius and convergence for these series. In case you forgot, we at the beginning of the unit talked about these series and when they converge and when they diverge. And now by the end of it, we're talking about series with x's in them. And we're wondering what numbers could I plug in for x that would still make it converge. This is us doing that, and we get like an integral and a radius of converging. That's the last thing we did. But now, is this it? Yeah. Now we are doing the last little section, which is basically that poster that's up there. That is just like representing functions as power series, which isn't actually anything really that new. Like this is what 10.6 was all about. But 10.6, I think we went from like, I don't know, we did 7 terms of the Maclaurin series. Now we're going to infinity. And we're talking about derivatives and integrals of series and stuff like that. But the idea of this isn't really anything that's new. So there's some stuff on here that is helpful. That first paragraph is talking about what I just said. But there are 4 that you have to know, 4 of these theories that I'm talking about that you have to know good. I'm hesitating because this is not letting me write your viewers. But where's the original? I'm viewing this because it's saved as like a copy. Whatever. Okay, we'll save this. Save. Now can I write? All right, there it is. Now I can write. Okay. So there are 4 of these that you should know, like without having to do any math. Just like you look at this function and you know it's Maclaurin series. So that would be e to the x sine of x cosine of x and 1 over 1 minus x. And these would, I mean, right now you probably don't remember them, but we've talked about all of those before in this series or this section, like just having practice on those series basically. Then this talks about how you could, if you get some sort of function that is not one of those 4 elementary functions that you should know off the top of your head, then how could you get a series for that function? So you could do all these 4 things. So substitute a series in for x, or sorry, substitute x into a series, or multiply or divide the series by a constant or multiple, or add or subtract 2 series, or take the derivative or integral of a series. All of this will make sense as we do examples. But, okay, first a reminder. This kind of has it in the opposite way than I would explain it. But remember at the beginning of the year, or sorry, at the beginning of the unit, we did these series, which were called geometric series, which converge if the R is between -1 and 1, basically. Okay. We also learned that these series converge, like we learned a formula for what these converge to. And that formula was this. It was first term over 1 minus whatever the R was. There it is. Remember that. If you don't, you could go back. Like it was the first section that we did, or the second maybe. But yeah, we learned that way back. Now it's coming back as function, because if you take this idea and you say you set a to be 1 and x to be r, well, then you get this geometric series that I'm circling right now. And so therefore, if x is between -1 and 1, then this series with an x in it is equal to this function. In fact, I wanted to have Desmos up for that. So let me show you what I mean. Here's the function 1 over 1 minus x. Normal function like that you know and love. Now what if I said, now take this function, the sum from 1 to, or from 0 to infinity. Desmos can't handle infinity, but let me do like from 1 to 50 or something, or from 0 to 50, I meant, of x to the end. You can see this blue function, which is the series, matches the red almost exactly. And it would be exactly on it if it was from 0 to infinity. However, no matter how far I go, like I said, the series that I'm highlighting right here will only converge if x is between -1 and 1, which is why after -1, look at 76, 89, 93, 98. That's when it starts to diverge, is when it gets closer and closer and farther from the convergent interval. You know what I'm saying? So after 1, this is not going to converge. There's no blue on this that I'm highlighting. There's no blue after -1 here. But within -1 and 1, the blue is the same as red. Okay. And so for that reason, you can represent the function 1 over 1 minus x with this power series, which is actually kind of it's like a kind of a helpful thing. You would think, oh, this is a very specific function. But I remember when I was doing like my master's degree, like research or whatever, like my master's project, this thing came up. So it's actually a very applicable thing, like even in higher math, that you see this function or some variation of it like that you'll see later. Okay, so keep this in your brain. Geometric series equal this. And so if you put a function, like if you're interested in the function with an x in it, then you could make a geometric series with an x in it and represent the function as that series. But what am I talking about? Here it is. Watch this. These are notes from last year. And I think they even printed on your paper as well. I forgot to erase those. But it says, find the power series representation for the following function and determine its interval of convergence. So here the function, notice it's not exactly, the function we were just talking about up there was 1 over 1 minus x. This would be this geometric series. That's 10. Okay, now the difference is this is 1 over 1 plus x. But the idea is, could I just alter this series that I'm circling right here and get this function? So do you guys see a way to do that?
Square.
Because why?
Square. Well, I would say square, but then you would have to x square.
Right, but why are you saying square? Yeah, exactly. Oh, you're just wanting this minus to become a plus. And so, what were you going to say on it? Oh, okay. It's actually, I think, easier than that. If you just made this, 1 over 1 minus negative x. Oh, then that's minus a negative and plus. And so now it turns into that. So this feels like cheating, but it's not. This is totally good, and it'll work. You can just make this a series of from 0 to infinity of, instead of x to the n, negative x to the n. And that's the answer. Although most of the time you would see this written as this, so that it's clear that this is alternating. You would see it written as negative 1 to the n times x to the n. I think you would see that more common. That's the same thing, just to be clear. This is negative 1 to the n, x to the n. Same thing over here. Cool. And then it said, oh, well, I want to say more about this, but let's finish the question. It says, find the interval of convergence. Well, okay, well, this is just a geometric series. I hope you agree. And so we just need the r, which whether you see that as x to the n or you see it as negative x to the n, same thing, because we just need r to be less than 1. So in other words, we need the absolute value of negative x to be less than 1. This would be the r value again. These converge if r is less than, or the absolute value of r is less than 1. That's from the beginning of the unit, which you may not have thought about since before spring break. But that's the truth. And then that in our particular case, that would mean this that I'm highlighting right here. And so therefore, if I do some algebra on this, first of all, absolute value of negative x is the same thing as positive x is less than 1, or between negative 1 and 1, I should say. There's the interval of convergence. Except I should kind of check the endpoints, but not really. Well, let's just do it. I don't really have to, because I know geometric series don't converge at the endpoint. But just to be consistent with what we've been doing in the past, I'm going to check what happens in the endpoint. If I were to plug in 1 into this negative x, then I would get that function, or that series, and this series does not converge. This is negative 1 plus 1 minus 1 plus 1 minus 1 plus 1, etc. And actually, we should talk about this in a second. I already spoiled that this does not converge, but you might be thinking, actually, shouldn't it converge? We'll talk about that in a second. And then if this was negative 1, then you would get negative 1 to the n. So in other words, you would get this here. 1 to the n, which is just 1 plus 1 plus 1 plus 1 plus 1, which of course, this one for sure does not converge. 1 plus 1 plus 1 plus 1 just keeps growing big time. No way would this ever converge. This one diverges. And this one diverges too, like I said. So this interval of convergence is good. I do not need to include the 1, and I do not need to include the negative 1. I'm saying a lot of math. Are you guys, is this coming back too slow? Okay, medium. Okay, so then maybe you're completely lost. I was assuming you would remember some of this. But well, now I don't know what this. What are you? If you're confused, do you have specific questions that I could clear up? Okay. All right. Here, let's talk about this one now. Let's talk about this real quick. How come I said that this? I have to do it on this. You guys don't have to write this. I just can't do some work on the side work, but then the video, people can't see it. But how come I said that this series divergence, you guys know? The -1 to the n.
It's balanced between -1 and 0.
That's the thing. Is that it starts off as 1 minus 1 plus 1 minus 1. And so if you stop, okay, remember, these converge, the definition of convergence means if you take the partial sums, like if you stop at the 1 millionth term, or the 1,000,001 or the 1,000,002, etc., blah, 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 and you see what those series approach, then it converges. But in this case, if I stop at an even number of terms, like for example, the fourth term, I get 0 and 0, so this would be 0. If you stop at an even term. But if you stop at an odd term, then you go one more, so it'd be 0, 0, and then 1. And so therefore, this does not, the limit of these does not, like, the partial sums go 0, then 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so then those don't approach any one particular number, meaning this does not convert. Although you might feel like, oh, shouldn't this be 0? No, because of what I just said. Cool. All right, is learning. Let us also learn visually. So watch this. Another thing I wanted to say. Here's us going back to Desmos. Here is us changing this function to what we wanted to model, 1 plus x. That's the red function. Here's us checking our answer. What if I made this not x to the n, but negative x to the n, like we said on our packet? Boom, matches it from where to where? Oh, from -1 to 1. So just like we said. Yeah. Nice. All right, you guys feeling decent?
Yeah.
Okay. Next one, then watch this. Says find a power series representation for this function now and determine its interval of convergence. All right, like I said, last one we just took this series that we already knew, the geometric one, and we altered it in some way. And the idea is the same for this one. It's just you guys are just now learning about what you can do to alter and what you can't do to alter. But again, my frame of reference is this blue function that I just wrote. I would like to get from this blue function to this G function over here. On the bottom, do you guys see a way to get from blue to black? By the way, this blue function, remember, is x to the n. So how could I change 1 minus x to 2 minus x? No, but that's, hold on to that for a sec. Jeremy said put a 2 in front of it. Like right there, put a 2. But that would not put the 2 down here. That would put the 2 like on the top. But that's a good idea for later. Over 2 might actually might kind of work, but you'd have to alter some stuff. Because then this would be 2 minus x over 2. Or something like that. Or it might be 2 over something. You should try that, because actually I think if you put this into Photomath, they do a version of what you just said.
Okay.
But that's not what I saw. What I saw is what if I change this x to something like this? -1 plus x. There. What if I did that? Then it still has the same form, 1 over 1 minus something, but 1 minus -1 will make 2, and negative positive x would be the minus x that I want.
X on top.
And then the x on top, let's talk about it. The x on top is what Jeremy was saying before, even though it feels like cheating. Here, let me make some progress on this, the answer to this question. So I know that instead of x to the n, I'm going to want this whole parentheses to the n. So -1 plus x to the n. And then what about the x on top? Feels like cheating, but yeah, just multiply by x. And there you go. Cool. Okay, I'll convince you of this in a second. And Jeremy's idea was also good about making this over to I don't remember what the actual answer for that would be, but you could have different series represent the same function. It's just I think Jeremy's is a little better because his interval of convergence is wider than what we wrote. But we'll talk about that in a second. Here is the answer. I'll show you on Desmos in a second, but it says find the interval of convergence. Okay, I will. This is kind of hard to see, but what I wrote in orange right here is a geometric series like we just talked about. I have number times like expression to the end. And so as long as this expression is less than or like between -1 and 1, then this will converge. Again, like geometric series. That's a geometric series that I just wrote in blue. That's exactly what we have here, although this isn't it's an X for A and it's a whole expression for R. But it's still got the general form of a geometric series. So this orange series is a geometric series, meaning that they will converge as long as that expression, our R, the thing playing the role of our R right here that I'm pointing at, as long as that's between -1 and 1. And so in other words, -1 plus X has to be between -1 and 1. And so now if I solve for the X, like what can X be? And I add 1 to all sides, +1, +1, +1. To get the X alone, I would get 0 less than X less than 2.
Wouldn't the -1 be positive though?
No, not like that. It's not taking the absolute value of something plus something is not the same thing as taking the absolute value of each thing. Just like with square roots and just like with like sine of something plus something and stuff like that. Just in general, pluses don't work nicely with other, like being inside other functions. All right, let me show you on Desmos after this question.
So when can you just like when it's in the A R to the N form, which is like the geometric series form, like A over 1 minus R, how often can you literally just take the like numerator or whatever and turn that into the X?
Every time, yeah.
Oh.
Yeah, I can't think of a time where you can't.
So you basically just have to figure out what you have to the bottom of all of it.
Yeah, and then multiply on top by whatever. Yeah. All right, cool. And then I think this is, I don't know, whenever I see it on Desmos, I'm like, okay, I'm satisfied with my answer. This is true what I wrote. So let's do that. It was X over 2 minus X, right? Okay. There's that function that we're trying to match. Then we said it should be X times -1 plus X to the N, and that would be between 0 and 2. You can see at 0, it starts to veer off, and around 2, it'll start to veer off. Like after 2, it does not have any blue on it. So we did good. Good job. This answer is good. Had we done it Jeremy's way? Let me see if I can figure it out real fast. I think it would look like. No, bro. Here, let's do some algebra real fast. Don't write this if you're good with your answer. But had we done it Jeremy's way, it would have been like. That would have been 1 over 1 minus X over 2. So get a common denominator, you would get, multiply everything by 2. That would be 2 over 2 minus X. And then I want just X up here, so times X over 2. So in other words, N plus 1. Watch this, watch this, watch this. Oh, right. Oh, that's okay. Watch that. Yeah, there you go. And so you get this. You get the same answer, I guess. Oh, but you get a way wider interval. Look at this one goes all the way to -2, from -2 to 2, whereas ours went from 0 to 2. So that's why I'm saying if you might get different representations, like Jeremy's answer in green doesn't look a lot like our answer in blue, but they're both equivalent, as you can see on Desmos. Like they both model the same function. It's just ours models it on a very narrow interval compared to Jeremy's, which models it on a wider interval, which is why I think if you put this in Photomat, they will prefer the green one. They will give you the green one because it's a wider representation of the same function. Cool. Yeah, okay, I think that's all I got to say about that. Questions? You guys, this reaching you? This is very, I mean, it's the last thing you learn in AP Calculus BC, so it's very difficult and abstract, but it's the last thing we're learning. So it's expected that you might be a little confused. That's fine. The more you do these, the better you get at them. All right, 31. Let's keep going then. If you have questions. Okay. All right, find the power series representation for this and determine its interval of convergence. I think this one is similar to the other ones enough that you guys should try it. So here it is. I don't know, 2.5 minutes to try this yourself. Again, try the same traces before. I think my frame of reference is this. How can I alter the bottom so that that becomes just a straight up 3x instead of 1 minus? All right, try it. Here's 2.5 minutes. Oh yeah, no. Yeah, there's something you don't remember about inequality that when you divide by negative equals stuff. So that's good. Yeah. Oh, this thing. Now, so just plug it in. Zero is button. Yeah. I think it's button. Yeah, that's what you did. Put that. Hey, what you say? What? Negative. Negative. Oh, no, his is right, because the velocity is negative, 1 over negative. That's the 1 minus. Negative. That one. Okay. Yeah, so, yeah. But I was kind of, it was some weird, we always got positive intervals. Basically. Okay. What did you, well, here's what I saw people do. Did anybody do something different than that? Because then this way, if I just change this x to 1 minus 3x, then 1 minus 1 is 0, and minus negative 3x is positive 3x. So you get what I want, what you wanted. But did you guys get something different? Okay, all right.
I did.
Well, I thought like a lot of you guys are editing right now. What went wrong with your? What is it?
I literally, I ended up writing the 1 minus before I was writing the theory.
Oh, okay.
So I kept the 1 minus of the.
Oh, I see. 1 minus all this.
Yeah, I just.
I guess. Yeah, you're just trying to replace this.
Yeah.
Other questions?
Yeah.
Okay. All right. Well, even if you got it wrong, hopefully you see what you got right now, or like what it should have been now. Here's what the answer should have been, or like one of the answers. Like I said, there might be a better one with a wider interval, but that's the most obvious one I thought of. And then it says find the interval of convergence. So again, you just need this to be between -1 and 1. So I need 1 minus 3x to be less than 1, go bigger than -1. You solve it for x, and that would be the interval. Okay, so let's solve it for x. If I subtract 1 from all sides, then you get something weird. You get -2 less than -3x less than 0. And then, well, I guess that's not weird, but what is weird is that when you divide by -3 here on all sides, then you may not have remembered this from Algebra 1, but what is it?
Flip the side.
Yeah, when you divide by a negative, you have to flip in an inequality, you flip the inequality signs, so that you get 2/3 is greater than x is greater than 0. So that's a weird way to write it. So more normal, you would write x is between 0 and 2/3. And that would be your answer. Nice. All right, and then now that I'm seeing this, I wonder if we'll need 3 days for this. Oh, yikes. Well, yeah, we might. But okay, let's get as far as we can. Are you guys good with this? Here's us checking on Desmos fast as lightning. Make sure we're right. 1/3, yeah. Get out of here, get out of here. We're trying to match that red function. We said it should be this 0 to infinity or to 50, I think. 1 minus 3x to the n. And it does match it. The purple is right on the red up to about 0.66. It should, 0.63, and then it starts veering off. And it would be closer, watch it. I guess I never talked about this, but it would be closer to 2/3 the more terms I add with it. So like if I went to, let's see how many you can handle it. If I went to 70, it would get closer than 0.63. It would be 0.64 now. If I went farther, it would get closer and closer to the 2/3 that we said the interval. Yeah. Cool. All right, and then let's see if we can handle one more, just for the sake of time. Because I don't want to, the faster we finish, the more we can review later. So I don't mean to overwhelm you with information. Hopefully this is making sense and you're catching on to that. All of these, though, were the same idea of how can I replace the x to get what I want on the bottom. Now we get this idea coming up, which is that if you know a series represents a function, and now you want to represent not the function itself, but maybe the derivative of the function, or maybe the antiderivative of the function, then that's a lot. You can do that. You can just take the derivative of the series or the antiderivative of the series, and it still represents a function. And the only thing that you have to like for this example, I don't even know how I just scrolled. That was crazy. I don't know how that happened, but I wish I knew. That would save me a lot of time. But anyway, if what was I saying? Oh, that you can take the derivative of a series and the antiderivative of a series. It's very helpful. Actually, that's how you get like natural log as a series. We'll talk about that in a second. But the thing you have to keep track of is that the interval of convergence may be different. The interval of convergence may be different, but the radius will be the same, meaning the endpoints may be different. Like if the endpoint of one, like if the original had these endpoints, for example, then the derivative may have these endpoints. Like not include the negative, the one or whatever. It's just the endpoints that might differ, but the interval is basically the same. So in other words, the radius will be exactly the same, but the behavior at the endpoint may differ once you take a derivative or anti-derivative. Okay, cool. In this packet, though, it just asks you for the radius of convergence, and so since you know the radius of convergence for the original, then you know the radius for the derivative or anti-derivative. 4 minutes. No, I don't want to rush through it. Yeah, let's just leave it there. Let's leave it there. We'll do this tomorrow.
Yeah. I got really worried for a second.